Ever get that feeling when you look up at the night sky and just think, what do we really know about what's out there?
Humbling, isn't it?
Totally. And today, we're diving headfirst into one of those big cosmic mysteries, dark matter.
Ah, one of my favorite topics.
Well, get ready because you've sent us down a rabbit hole of fascinating research with this paper on something called Electroweak skyrmions. I'll admit, the title alone had me a bit lost.
It's a mouthful, I know. But the concept, trust me, is even cooler than it sounds.
Okay, you've got to give me a starting point here. When I hear skyrmions, I'm picturing like spaceships or something. What are we actually talking about in the world of physics?
All right, imagine this. You've got a silk scarf,
Hmm.
and you twist it, tie it into a knot. That stable, twisted-up configuration. That's kind of what a skyrmion is. Except instead of silk, we're dealing with energy fields, the fundamental fabric of the universe itself.
Okay, so a knot of energy, but this paper gets even more specific, electroweak skyrmions. That's got to be a clue, right? Links to those fundamental forces of the universe.
You got it. The electroweak part, it points back to the very early universe, fractions of a second after the Big Bang, when two of the forces we know today, electromagnetism and the weak force, were actually unified as one.
So way back before things cooled down and split apart, but how do we even study something from a time period we can't even replicate?
That's where the fun of theoretical physics begins. We use mathematical models, theories, to take what we do know and try to make predictions about what might be possible. And in this case, the researchers, they're using something called the Higgs Effective Field Theory, HEFT for short.
Okay, HEFT, I think I've seen that acronym before, but my brain goes straight to weightlifting, not particle physics.
Right. Well, think of the Higgs field like a vast ocean that permeates the universe. This ocean, it gives particles their mass. Now, the Higgs boson, that particle we discovered back in 2012, that's like a ripple in this ocean, HEFT basically lets us study the aftermath of those ripples, understand how the Higgs field interacts with other particles in ways we hadn't really considered before.
So we're zooming in on the ripples in the Higgs ocean, seeing how they mess with everything else. And this ties into those mysterious skyrmions, HOW.
Because what this paper suggests, it's that within this HFT framework, under the right conditions, those knotted up energy configurations, our skyrmions, they could actually exist as stable particles. Tiny, far smaller than an atom, but potentially with a huge impact.
Okay, I'm getting a serious, this is a big deal vibe here. But how do we go from a theoretical framework to proving these things are actually out there? It's not like we've got a test tube of skyrmions, right?
Not quite. Directly observing them, that's the challenge. They're incredibly elusive. Imagine trying to study a firefly, but it only flashes for a fraction of a second in a massive dark forest.
So where do we even start looking? What are the clues, the breadcrumbs that these skyrmions might leave behind?
And this is where it gets really cool. They've identified specific operators, think of them like instructions or rules for how particles interact. Two in particular called CD1 and CD2 lower. They're crucial for skyrmions to form and be stable in this HEFT framework.
So these operators are like the recipe, and the skyrmions are the cake.
I like that analogy. And
Yeah.
the paper, it's laying out the ingredients, the baking instructions. It's saying if we find evidence of these operators acting in a certain way, it could point right to electroweak skyrmions existing.
Okay, so we're on the hunt for these operator fingerprints, but where do we even look for something on such a tiny scale?
We go big. I'm talking about the Large Hadron Collider, the LHC. By smashing protons together at nearly the speed of light, we create conditions extreme enough that, just maybe, we could produce these skyrmions.
So we're recreating in a tiny, controlled way the kind of energy that existed right after the Big Bang. Mind officially blown.
It's pretty wild, right?
Mhm.
And while we haven't directly observed electroweak skyrmions in these collisions yet, the search is on. And the more we understand about these hypothetical particles, the better we'll be able to spot them if they do show up.
We've got the theoretical foundation, a potential smoking gun with these operators, and the means to search at the LHC. What have we found so far? Any hints that we're on the right track?
Well, that's the million-dollar question, and what we're going to dive into next. This paper goes beyond just theory. It actually looks at experimental data, trying to find those skyrmion fingerprints. And what they found is very interesting.
So we're sifting through data from the LHC, trying to find evidence of skyrmions. But how do we even know what to look for? What would a skyrmion signature look like in that sea of particle interactions?
Okay, so remember those operators, those CD10 and CD20, the ones crucial for skyrmions to even exist? Well, they don't just dictate whether or not a skyrmion can form. They actually influence how those skyrmions would interact with other particles, as if they're there.
So even if we can't see the skyrmions themselves, they might leave a mark, change how other particles behave in a detectable way.
You're getting it. Think of it like, trying to figure out if someone walked through a room. You might not have seen them, but maybe there's a faint scent, their footprint, something's a little off. We're looking for those subtle anomalies, those deviations from what our standard physics models would predict, because those could point to something new, something like a skyrmion being created in those collisions.
I'm with you so far, but isn't physics at the LHC incredibly complex?
Yeah.
How do we know a weird signal isn't just, I don't know, some other exotic particle or interaction we haven't accounted for yet?
That's the million-dollar question, and it's what makes this paper so exciting. They didn't just stop at, hey, maybe skyrmions exist. They dug into real data, crunched numbers, and actually compared their theoretical predictions to measurements from LHC experiments.
So they have a target in mind, not just throwing darts in the dark. Did they hit the bullseye? Did the data match up with what they'd expect if skyrmions were playing a role?
It's more like they found a cluster of darts, really close to the bullseye, but not quite a direct hit. Yet, at least. This paper, they focused on something called anomalous quartic gauge couplings, AQGCs for short. Now, these AQGCs, they're very sensitive to new physics, anything beyond our current standard model, so new particles, new forces, you name it.
So QGCs, they're like our alarm system going off if something really unexpected is happening in those collisions.
Exactly. And what they found is that for certain ranges of those operator values, CD10 and CD22, the ones crucial for skyrmion stability, the experimental limits on those AQGCs are getting really close to the values predicted IF skyrmions exist.
Okay, so not definitive proof, but we're seeing these hints, these suggestions that maybe, just maybe, the skyrmion hypothesis is on the right track.
Think of it like those blurry photos of Bigfoot, not conclusive, but definitely makes you wonder, keeps you searching. We're in that exciting phase of science where the theoretical and the experimental are starting to weave together.
This is what really blew my mind when I first read this, the whole skyrmion dark matter connection. The paper suggests electroweak skyrmions could actually be a dark matter candidate. Unpack that for me, because what is it about these tiny knots of energy that makes them a potential fit for something as elusive and mysterious as dark matter?
It comes down to a few key properties that make skyrmions a surprisingly good fit for what we know about dark matter, or rather what we don't know about it. First off, dark matter doesn't interact with light. That's why we can't see the stuff directly. It's like a phantom, only detectable through its gravity. And electroweak skyrmions, at least as sort as we currently understand them, they interact very weakly with other particles, including light.
So they're kind of like tiny cosmic ninjas slipping through the universe unnoticed. What else makes them a good fit for this whole dark matter puzzle?
Well, we know dark matter has to be stable. Like, really stable, right? It's been around since the early universe, holding galaxies together. And those electroweak skyrmions, those knots of energy, they're predicted to be incredibly long-lived. Potentially, we're talking longer than the age of the universe itself.
Okay, so we've got stealthy, we've got staying power, but how do we go from could be to IS? What's the smoking gun? The evidence that would convince even the skeptics that we've cracked the dark matter code?
It's a multi-step process, right?
Yeah.
For one, we need more precise measurements of those AQGCs, those specific interactions at the LHC. If we start seeing deviations from the standard model, but they consistently line up with what's predicted FRR skyrmions, well, that would be huge EE.
More data from the LHC is key, but are there other avenues, other ways to investigate this whole skyrmion dark matter connection?
Definitely. The LHC, it gives us a glimpse into the subatomic world, but astrophysical observations, they're crucial too. For example, if skyrmions really DO make up dark matter, there should be a specific imprint, a signature, in the cosmic microwave background radiation, that faint afterglow of the Big Bang.
So we're talking about looking for clues at both ends of the universe's timeline, the very beginning, A and D, the present day.
Exactly. It's a multi-pronged approach, and there are already some observations, some hints that, while not conclusive, suggest skyrmions might be playing a role out there in the cosmos. For instance, the way galaxies rotate, how they're clustered together. There's some anomalies, some things we can't quite explain yet. And skyrmion dark matter, it could potentially provide an answer.
It's like we're piecing together a giant cosmic jigsaw puzzle. We've got a few edge pieces, maybe even a glimpse of the center, but a lot of the picture, it's still missing.
That's a great analogy. But the exciting thing is, the search is on for those missing pieces. Every new experiment, every theoretical breakthrough, it brings us one step closer to understanding what our universe is really made of.
Well, I have to say, after this deep dive, I'm even more in awe of the universe than I was before. Who knew something as seemingly abstract as a knot of energy could hold the key to such profound mysteries?
That's the beauty of science. We question, we explore, and sometimes the answers are even more mind-blowing than we could have imagined.
That wraps up our deep dive into the world of electroweak skyrmions and their potential link to dark matter. It's been a journey from the tiniest particles to the largest structures in the universe. If you're as intrigued by all this as we are, be sure to check out the full research paper. We've got a link for you in the show notes. Until next time, keep looking up and keep those questions coming.